Hello, this is Keao Caindec with Mocana, and welcome to the Mocana webinar today on automated security lifecycle management. And today we'll be talking about automating certificate management. Certificate management is one of the most complicated aspects of securing IoT that we run into with some of our industrial customers, for whom it's a bit new. And today I have with me Dean Weber, our CTO at Mocana. Welcome, Dean.
Welcome.
All right. So just a quick intro on Dean. Dean was previously the CTO of CSC Global Cybersecurity and has had a view into all aspects of cyber. He's also been at several companies acquired by Citrix, Applied Identity, and Teros. He's also spent a lot of time in both commercial and defense sectors, in both advisory and implementation. Dean is also frequently speaking at a number of industry events and various standards bodies. Great to have you, Dean.
Thanks for having me.
You bet. Okay, so jumping into a little bit of the context here for certificate management. I think fundamentally when it comes to IoT or industrial control systems, factory automation, transportation, there's always this question of, well, these attacks are crazy, and how do we really secure IoT? And what we see is there's still a gap between the mindsets of focusing on trying to defend and protect and respond to incidents versus really ensuring that fundamentally the devices and the systems themselves are trustworthy. Now, easier said than done. I think when we look at the challenge of securing the Internet of Things, a lot of it comes back down to the supply chain. So, Dean, I'd love to have you provide us with your perspective on what needs to go into thinking about securing the supply chain, the components and software and hardware that goes into all of these devices.
Sure. Well, just like the devices themselves, there needs to be a concept of some level of root of trust, and in the concept of trustworthy computing, supply chain becomes an integral part of building those trust chains, so that the components that can go into the devices, or at least those that are electrically active or electronically active, such as processors, storage and memory arrays, etc., and as well as all of the code, BIOS, boot structures, etc. All of that can be built into a cryptographic supply chain where you can establish the trustworthiness of the platform based on all of the pieces that came into it in order to make it, and then current measurements of how that system exists. So the supply chain itself is actually able to carry forward on the various assembly components. If you have a chip like a TPM that's signed by the manufacturer, and then you have a subsystem where the TPM is in use with the processor, and that's a subsystem signed and endorsed by the TPM, and then on up through the system manufacturer, and then into the operating system, and ultimately up through the application and application executions. Those are all signed elements that go together to make up a system. And using X509 trust chaining, we can actually establish that trust chain and the efficacy of those elements, that they have not been modified since they were delivered by the manufacturer without authorization to be modified through things like update, from end to end. So from the initial platform builds all the way up through the transfer of ownership to the actual owner-operator.
So what I'm hearing is you really need to start during the development phase and bake that in, from the hardware integration, a root of trust, and also using trust chaining. And I guess fundamental to that is the identity of the device. How do the identity of the device, the different forms of identity of the device, related to what we call digital certificates?
Well, so digital certificates make up the backbone, the core elements of that signing. If you look at whether it's NIST 800-171 or ISO IEC 62443, a lot of the compliance objectives are now coming to realize that all of the discrete components that can be signed should be signed, and there are hash values established as a function of that signing. And then the certificates associated and the PKI associated with those signing functions all needs to be brought to bear in some mechanism that can effectively manage all of those elements, both from a chain perspective as well as from a value perspective of what those various elements' values are. And then tertiary to that is some mechanism by which you can establish that those values have not been modified. So it's a change in the paradigm of how we look at traditional IT security, which is a detect and respond, if you listen to Gartner and others, to morphing into a protect model, whereby you establish what the baseline is and you hold that system to the baseline using cryptography established based on X509 certificates and PKI infrastructures associated with those certificates.
Got it. And from a supply chain perspective, being able to do that in the beginning, ensuring that that device has a strong, secure, trustworthy identity, certificates that can be used to validate the identity, the components on the system, is important as it goes through manufacturing and also activation in the field by a customer, and also updates and management, because all of those functions, updates, activation, enrollment, that all will tie back to really the how high your level of assurance is in authenticating that device, which is going to be based on development.
100% correct. And in addition to that, that can then be tied directly to risk, so that you can establish your security profile, the efficacy of the supply chain, as well as the trustworthiness of the platform, which includes that supply chain validation,
right,
against the risk factors associated with a particular element.
Okay, so let's, we talk a lot about authentication, and you read things. Even the state of California recently passed some new legislation requiring that IoT devices use unique passwords and have two-factor authentication. And I always look at those and think, it's a recommendation, but it's not going to really do a lot, given if people really want to crack and attack that device. So let's talk a little bit about the different ways device designers build authentication into their products.
Sure.
Tell us about that. Yep.
So, I mean, the California law just said that you have to have strong passwords. Describing what a strong password is not really super conducive to strong security, because the strongest password is still pretty much vulnerable to dictionary-style attacks. There has to be more than just username, password, or just password by itself. I think what California is trying to do is say that the default password should be changed when the system is first brought up, and the manufacturer's default password should not be easily guessable or repeatable, which is a valid objective, right? I mean, that's all steps in the right direction. But again, as you just pointed out, I think we're going to find that people are going to misinterpret what the goal of that objective is, and therefore not really take it into consideration. Two-factor is a great example of that, in that most people think of two-factor as being two elements of authentication, when the reality of two factors is two separate values of authentication, meaning something you have, something you are, something you know, as one type in each element that you should be bringing to the table. And most people don't do that just because it's not easy to accomplish. You know, at best you'll have one factor associated with a VPN and another factor associated with the device authentication, and that isn't really two factors on the device. That's one factor per each. So when we get into these, we find that there's lots of shortcuts and there's lots of hit the easy button efforts to try and make it easier to consume the products or easier to use the products, and that includes things like pre-shared secrets. Pre-shared secrets, pre-shared keys, are a fine way to establish bidirectional communications mechanisms if indeed that is the goal. But there should be authentication that is independent of those two pre-shared secrets that are established between two elements, in the fact that there's no validation that either one of those platforms is trustworthy. All there is presentation of a pre-shared key or a pre-shared secret. So ultimately, this is what comes down to the digital certificate concept. You know, X509 is a characterization of how PKI is implemented and formatted in a particular environment. And there can be a combination of pre-shared secrets and asynchronous functions in a given certificate. There's also many different types of keys associated with PKI and certificates, where you can have endorsement keys, you can have signing keys, you can have transport keys, you can have platform keys, you can have all different function sets associated with individual or multiple key pairs, which strongly establishes not only the efficacy but also the identity of those devices in a bi-communications mechanism, whereby I can establish that you are trustworthy through your use of key sets, and you can establish my trustworthiness through my use of key sets, and then we can ask each other to exchange values so that we both know that the other one is trustworthy before we actually start to communicate.
Yeah, I mean, it's sort of like continuing to delve down into why should you trust that? Okay, you have a password. Why should you trust the password? Well, it's strong. Well, why do you think it's strong? You know, same thing as you dive into each of these with pre-shared keys or digital certificates. So much of it ends up going all the way back into how much do you trust the root of trust that you're building this around. And clearly with password, two-factor, pre-shared keys, there is a lot to be desired in terms of actually trusting the source of authentication.
Or destination, either or both.
Right. So, okay, digital certificates have a role. We see it used in everything day to day, from your browser to a website, PKI. So let's just jump into some definitions and background info. What exactly is a digital certificate?
Now, as I said, what a digital certificate is a published framework of the use of PKI in a particular architecture. The types of keys, the strengths of keys, the algorithms associated with those keys, as well as key strength and length, the various aspects of those key architectures. As I said, you may have signing keys and you may have transport keys, or you may have platform keys and you may have root of trust keys, or other forms of endorsement functions, AIK type functions, where the key sets all have a defined purpose. There is a public-private sharing. I mean, the wonders of modern mathematics is that the way PKI works is there's a public key and a private key. The public key can be shared. The private key should be protected. A person who has your public key can then use that public key to encrypt something that only your private key can decrypt. And all of that is described in the certificate itself.
Right. I mean, it's it's what you described, and that gets you to the point where you can actually exchange something that you both feel is a secret that you both have.
If pre-shared secrets is the the most efficient model in which to establish that communication. The value proposition of pre-shared secrets is they tend to be much smaller. They don't have to withstand internet strengths or internet challenges against those strengths, where basically anybody can try to do anything with your key pairs. Once you set that established value between two elements, that you can both trust that value, but you have to get to that point first. You shouldn't just roll to that point right out of the gate.
Right. You kind of talked about this earlier, about the different types of certificates, some that can be used for signing, some that can be used for encryption. You can certainly use these not just for, say, SSL communications or encrypting communications or even PKI, but you can also use it for trust chaining. Can you talk a little bit about how certs can be used with trust chaining and kind of validating that nothing has changed on a platform?
Absolutely. So again, when you use a signing key to establish the identity and the function, meaning the hash value of a particular element, be that hardware, firmware, software, whatever, that's a very specialized key. A signing key is a very specialized key used for the purpose of creating a value, a hash value, and signing that value as being appropriate given the type of measurement and the type of hash being used. Once that's accomplished, then the concept of trust chaining can be brought to bear, where two or more signed elements can be chained together. And the way you do that is through the use of another set of specialty keys called endorsement keys. And what the endorsement key allows you to do is to say, I'm value 1, and I've now been given value 2. So what I'm going to do is I'm going to endorse value 2 against my value 1. And what I come up with is a net new value, a net new hash, and a net new signature based on that endorsement that says these two elements have a cryptographic affiliation, and these are the values associated with that. And when you bring that into an element like a TPM to BIOS, BIOS to first stage, second stage bootloader, and on up through utilities, kernels, applications, whatever, all of those elements are then chained together so that that top level, that last endorsed value in hash, represents the cryptographic trustworthiness of all the things that are in the measurement, meaning all the things that have been endorsed. And each one of those elements is then signed, and then each one of those key pairs that are associated with things like platform and transport and storage, all of those functions can also be brought into the trust chain so that you have a cryptographic representation of the trustworthiness of the system that is immutable based on those measurements. Now, immutability really depends on the strength of root of trust, but at the end of the day, you can make a claim that I am trustworthy because these elements have not been changed, and you can go back and ask for a remeasurement or a manifest of all of the elements that are being put together in order to say this is their original value, this is their current value, and those values are equal, therefore nothing has changed, therefore I am trustworthy. Does that make sense?
Yes. Yep, absolutely. Absolutely. I mean, if you have a strong root of trust on the device and you're using certificates for more than just authentication, you can use it for trust chaining and really begin to ensure that the device itself is trustworthy, not just the other entity or machine or user that you're communicating with.
That is correct. And then, there are mechanisms like the TPM query and nonce where we can establish bidirectional authentication validity between those two elements by asking the remote element to say, are you trustworthy, what are your values, and have that work bidirectionally where you then query me or ask me, am I trustworthy and what are my values? And we can establish a basis for trust through remote attestation to say that we are both trustworthy because we know each other's values and they are appropriate, and we can do that before we actually start communicating and setting up those pre-shared secrets as you discussed.
Right. Now, provisioning, so working with a CA, a certificate authority, like a Global Sign, DigiCert, VeriSign, or even if you're running Microsoft CA in-house or NDES. How can you talk a little bit about what the user is doing? Because it always surprises me how manual this process is of using a commercial CA. And once we go through that, I'll ask about self-signed certs and how they're different. But step us through how the user really makes that request to a CA to get a cert.
Sure. And there's a very well-defined request structure associated with what you want the cert for, are you eligible to receive the cert, and what values need to be part of that cert. Remember, the cert is a representation, a format of all of the PKI associated with a particular certificate, which can also include multi-factor, it can be multi-value, it can be multi-type, meaning that you could have biometrics, you could have one-time password generation, you could have all kinds of things that are associated with that element. But the certificate itself has to be established based on a policy, and that comes from the CA itself. The user requesting the certificate or the device requesting the certificate has to have an authorization to request. Once that is established, then the certificate is created associated with the root of trust or trust authority, that is the certificate authority or elements of the certificate authority like a registration authority, where then that certificate is presented back to the requester. And all of that is actually pretty easy to do in terms of process. Where it gets hard is how do I use that? How do I get that involved in something? Which is why so many organizations, initially anyway, have found the use of public key infrastructures and certificates to be difficult because there aren't automated processes associated with the utilization of those certificates, not so much the creation. Also why self-signed certificates, which I guess we're going to talk about next, actually come into play, because people don't want to have to go through even that relatively lightweight process to get a root signed certificate.
Right. I mean, the self-signed certificate is sort of like you have your public key, and then you request, something manual or in-house. You request a certificate based on that public key, and then you yourself sign it.
I'm me because I say I'm me.
Right.
That's very trustworthy.
Yeah, right. Yeah, it's
depending on who you are, of course.
So I think there are a couple of issues, and we can talk a little bit about those, but just highlighting it here with this image, right? One is it can be a very manual process. You're using oftentimes an IT administrator is making this request on behalf of a device and then pushing that certificate back into the device. All kinds of issues with the administrator then potentially having access to the private key and thereby being in a position to compromise that key or sell that key later. And then also just scalability, the manual nature of SCEP and OCSP can be challenging for companies that are in the IoT space that need to scale and may not always have that trustworthiness of a field tech or a tech in a factory.
Well, and as I mentioned, the creation of the certificate is not difficult. The utilization, the implementation, the enrollment of that certificate onto a device or into a device at manufacturing time is where things get much more interesting. And over the years, we've tried various methods ranging from proprietary through open standards like SCEP and OCSP to do certificate management on elements, but none of them have really solved the problem yet. So, SCEP is a great way. A simple certificate enrollment process is an easy way of contemplating how to install the certificate for use in a device. But the problem is that the SCEP protocol itself is very insecure. Mm-hmm. So, if you don't do that in a very secured environment, then you are automatically putting yourself at risk because the SCEP process itself is not very secure. It's simple, but it's not very secure.
I'm just going to touch on what you talked about earlier, that certificates are much more than just a way to identify or validate that the public key and algorithm associated with that public key is valid, but you can also incorporate all kinds of information and use extension fields to really have that certificate be able to identify what that, you may be able to link it to things that are important to your domain controller. What group is this certificate a part of, or what have you. So certificates can be very powerful in that way when linked to other business systems of the customer as well, for extended authentication, for example. Okay, so let's dive into some of the challenges. We've talked about certificates, what they are. We've talked about kind of where we see some of the big gaps. Step us through kind of where you see some of the biggest challenges in the enrollment of the device, kind of the manufacturer, and then the initial activation and overall management of that device. Where does this break down today?
Sure. So, again, at the beginning, we've already talked about SCEP, and the shortcomings of SCEP is that either you have to bring the device to a secured SCEP enclave to install the certificates, or you have to take SCEP to the devices in secure fashion to install those certificates, which even unto itself is not super bad until you understand that you actually have to manage those certificates as well. They have expirations. They change algorithms. They change key lengths and strengths. They change key types. And as we enter this pre-post-quantum world, things are going to accelerate as we start considering and contemplating how to use quantum-resistant architectures, given the fact that current thinking along the quantum process is that, an RSA 1024, 2048 length key is going to be able to be decrypted unofficially by a quantum process in seconds. So, the things that we use, the keys that we use to protect ourselves are going to quickly become obsolete in the presence of a quantum process, and we're going to have to address those. So, back to your question, the concept, first of all, is how do I get the key onto the device, which is great. Second is, once we get the key onto the device, how do we use it? So the enrollment process, remember we're talking about the potential for multiple key architectures from multiple providers that may or may not be chained together, that have to be utilized or should be utilized in the overall enrollment process. And this is where folks like Intel and EPID, the Enhanced Privacy ID key, where they're building key sets that are used specifically for the enrollment process to get a unique identity onto the device, a UUID that is known to the manufacturer, in this case Intel, onto the device, which is a form of a key set, but really not a key set per se that can be publicly used. We still have to associate that with other key functions. So at the end of the day, we've got the problem with manipulating the keys on the devices, installing, enrolling. Once we have the devices identified on or in an environment, how do we utilize those key sets and PKI architectures in order to create a secure process? And then tertiary to that is, how do we establish management of those key sets? I mean, if you look at, SHA-1 has been broken for more than a decade, right? We've known it's been broken. It's been broken a long time. There's all kinds of recommendations from all different types of walks of life in the cryptographic world to say don't use SHA-1, and yet the United States government, as an example, is probably still the single largest abuser of that because they can't get to the certificates to manage them. They're embedded certificates. There's no management process or processes associated with changing those algorithms or changing those key sets so that they don't use the SHA-1 algorithm. So these are all things that have to be brought into play when we talk about the end-to-end life cycle of a key set and the utilization of that in a secured environment. That makes sense?
It does, and we do see those scenarios with our customers in the healthcare sector. A lot of old equipment where they struggle to figure out how to upgrade the certificates on there and algorithms, as well as industrial devices today. So really important
to get that
right
just
from the
popped
beginning.
up on what is SCEP. SCEP is Simple Certificate Enrollment Protocol.
Yes. Okay. So just kind of summarizing here, we've talked about some of the challenges around, fundamentally a lot of this comes down to having a strong root of trust, challenges with self-signed certs, whether you're using pre-shared keys or SCEP. There are always greater risks of man-in-the-middle attacks when the administrator or tech can actually get access to the secrets, and just the manual nature that you just talked about with SCEP and the challenges with enrollment and ongoing management. And then fundamentally, that through all of this process, it boils down to there are challenges with just the weakness of being assured that their authentication is strong and that you can attest to it, the identity of the device. So let's dive into Mocana TrustCenter and talk about how we think about automating certificate management and another way of approaching certificate management and enrollment. Take it away, Dean. Talk to us about kind of the components and how TrustCenter can facilitate and interoperate with CAs.
Okay. Well, and TrustCenter is a Mocana product that is designed to be that interface subsystem between the root CA and the certificate authority itself, or the HSM, where HSMs are involved in lieu of or in addition to certificate architectures. It gives us the ability to automate the process of creating the certificates based on roles and policy. It gives us the ability to deploy those certificates securely over the wire or over the air using a relatively new RFC 7030 called Enrollment over Secure Transport, which solves for the trustworthiness of SCEP problem in the fact that it's basically SCEP on steroids over the air or over the wire. And we do that through an agency on the endpoint, which then also integrates the certificates into the various components, meaning that we establish the trust chains, we can manage the trust chains, we can manage the certificates involved in those trust chains through an agency. And then, as we talked about earlier, the idea behind update, where as you make changes to those systems, in the old models, you basically had to bring the system either back into a SCEP enclave or take a SCEP enclave to the device, which caused no end of problems when we talk about overall system management from a trust perspective, where our protocols allow us to do that very efficiently over the wire, over the air, in a policy-based format that can be almost completely automated.
Mm-hmm. Yeah, really powerful because the automation allows you to scale. It also provides a secure way of provisioning certificates where you don't have many of those challenges of admins, sysadmins, or field techs ever having access to the private key. The enrollment client can make that request to the EST service, and that on the back end can connect to the CA and return that certificate back to that device. It's automated, much more scalable for IoT, and importantly, reduces the chance of someone compromising private keys on a device.
Well, and while we have, potentially a few billion IT-level devices out there and users associated with those devices, when we start talking about IoT and IIoT, we're talking about tens or even hundreds of billions of devices.
Yeah.
So the problem is just exacerbated astronomically when it comes to certificate management on embedded devices or on integrated into other subsystem devices. in the industrial space.
For those of you who are not familiar with Mocana, we have built this on two components: Mocana TrustPoint, which is endpoint security software. It's very broadly used within the industry. It is software that we provide in the form of source code and binaries. It's protecting more than 100 million devices today across the major OEMs and manufacturers. They integrate us into their products, and we're integrated across 70 chipsets and the various real-time operating systems and operating systems. TrustCenter is a server-based platform. So this is about automating the security lifecycle, zero touch, one touch, automated security, and tools to help with both enrollment of the device and management of those certificates through to end of life, and also securing the updates of that device. We have put this in place with a number of we also have demonstrated zero-touch enrollment with one of our partners, Intel. But if you would like more information about how to do this, how to demonstrate this, how this would be integrated with your current CA and certificate management processes, we'd be happy to talk to you about that. And we think it solves a lot of the challenges that we talked about earlier in just automating this whole process and scaling it. So once the ID is on the device, that endpoint is much easier to enroll and activate within for its security lifecycle. So, you know, with that, the TrustCenter service itself comes with a dashboard. We're not going to go through and demonstrate TrustCenter per se today, but we do want to leave some time here for questions, and we'd be happy to answer any questions about Mocana or certificate management. Any questions you may have, even if you're new to this or trying to upgrade the way you're handling certificates today. You can issue that through the chat function on your within the UI here. Okay, so we have a question about the supply chain. So how do you secure how do you provide the certificates and tie it to a secure boot function?
To a secure boot function, you would, establish whatever the root of trust, whether that's a hardware or firmware or software-based root of trust, TPM, TE, trust zone. EPID is a form of a trust anchor, and then tying the certificate to that function. And then the signing certificates may come from additional vendors, or it may be provided by the OEM, or it may even be required usage by the consumer. But one way or the other, you're going to have signing keys associated with the various elements. They may be on the same root authority, or they may be on multiple root authorities, multiple discrete root authorities, where we need to have knowledge of, does that root authority have authority, and does this certificate come from that root authority? And we can do that through affiliation validation of the signing certificates themselves. So in that case, what you have is you have a root of trust with a basic element associated with some level of immutability. That element then uses an endorsement process to endorse the value of the BIOS, as an example. That becomes a net new value, which is the root of trust plus the endorsed value of BIOS. And then we endorse a third value, which would be the first stage bootloader, which could come from a third signatory or could be induced by the first signatory. All of these can be in various stages, how we link them all together. But at the end of the day, it's the endorsement process. It's the actual X509 trust chaining, which is a described process in the protocol itself that allows us to say, with these specific key sets, I can take these root signed, I can take these elements signed, I can take these applications signed components, I can chain them together using the endorsement process, tying that all the way back to a root of trust on a particular element or platform.
Great, thank you. And the other question is Mocana a certificate authority?
Mocana is not a certificate authority. We establish protocols with certificate authorities, HSMs, MIMs, SIMs, various elements of roots of trust, both at the device and at the services level, but we in ourselves are not a certificate authority and are not actually a certificate management system per se as described by the industry. We are an intermediate service between the device and the certificate management services at the back end.
Okay, here's one. So TrustPoint would need to be built into the embedded device from the start, correct? How does it then securely download a certificate? Does it have a built-in 509 certificate as well? How does TrustPoint make sure the associated server to download the cert is valid?
Okay, so TrustPoint by itself is the trust establishment of the device itself. In order to participate in the trust chaining associated with multiple back-end certificate authorities, we also have to have TrustCenter. TrustCenter is a service. So you're correct, TrustPoint needs to be built into the device, but the trust services framework sits in between the certificate authority or the HSM or combination thereof and the devices themselves. The enrollment process, which is how we establish that the key sets are valid and or establish additional provisioning mechanisms within those structures, where we may start with a root certificate through the enrollment process. We may want to bring additional values or additional components into that trust factor, similarly to transport keys or storage keys or platform keys that are associated with a particular platform or architecture that then have to be requested. That is through an agent technology that we have for enrollment that then talks to the back-end services, TrustCenter, that then allows us to provision the additional certificates onto those endpoints and link them together using a trust process, such as endorsement.
Right. So another way to think about this is, how does the certificate get on the device? The enrollment client, you could, from TrustCenter, send a command to the enrollment client to request a certificate. The enrollment client would do something like use the ID on the device, the UUID, maybe it's a TPM, maybe it's a GUID. It would take that, it could create a public-private key pair and submit the public key through the enrollment service to the certificate to the CA that would then confirm it. All of that is automated, and that's how it would get the certificate onto that device. So that's one way that you can get a certificate onto the device. And notice that the enrollment client is the one that can generate those key pairs rather than having an administrator do it. So it's an approach that's a bit more secure than having a separate entity generate public and private keys and pushing those onto the device.
Yeah, and also to the second part of that question, how would you know that the certificate back end, the certificate authority at the back end of TrustCenter was valid in issuing certificates and PKI to the endpoint? That can be done either through a zero-touch process where the establishment of the identity of the device is done by third party. In the case of Intel, EPID, and secure device onboarding, that would be a zero-touch model where we are given the UUID through an intermediate process, or it would have to be established on the device when we deployed the client or when we asked for the client. There would have to be something unique about the device, which is why that would be a one-step process. It would not be fully automated. We would still have to have some level of knowledge associated with that endpoint that could be revalidated by the service and vice versa.
Yes. We are out of time. This whole area is so interesting, and I know many of you may have questions. So please reach out to us. Go to our website, Mocana.com. Contact us. We would love to talk with you and see if we can help you. to upgrade security, answer questions, and provide some clarity to this very fundamental and important question to securing the Internet of Things and industrial control systems. So thank you for joining us today, and please be sure to join us again and keep an eye out for more webinars from Mocana, and have a great rest of the week. Thank you, Dean.
Thank you, and thanks all for listening.